Okay, let's settle down and get started. People are still coming in. That's good. Well, welcome to digital circuits, or design of digital circuits and computer architecture, which is really a continuum. I hope you're here for this. I'm Professor Onur Mutlu. As you can see over here, I'll introduce myself later on a little bit more. But today we'll have some fun. We'll figure out some mysteries in computer architecture if we get to it. But let me start with something that some of you may know, and I'll ask you a question. How many of you have seen things like this? Okay, that's a sizable fraction. So basically, you will learn why these things happen at the end of this course, maybe even earlier, actually. And I'm not going to tell you what these are, so you can search for them. Well, maybe I'll tell you. These are two major security vulnerabilities that were discovered very recently. Actually, January 3rd, 2018, they were reported, that exist in almost all modern microprocessors that we have in our systems today. It's in here, it's in here, it's in the data centers. It's pretty much everywhere. You can bet on it, especially this one, actually. This one looks evil, right? Doesn't look that nice. By the way, these are official logos. They're actually free to use. So you can use them however you want. But we will see them, and the basics that you will learn in this course will make you understand them and appreciate them a lot more. Because these are not easy things, actually. These vulnerabilities have been there for more than 20 years, more than 2 decades. But it took a while for people to figure out how to actually exploit them. So what is a vulnerability? Basically, somebody can steal your password or whatever secret data that you have on your computer reasonably easily, I should say, because of the way a microprocessor executes programs today. And I will later talk about that. The vulnerability is really due to what's called speculative execution, which is doing something before you actually know that you're supposed to do it. You need it. So you guess, and you execute some part of the code. If your guess is incorrect, you've executed something you're not supposed to execute, and it may bring in some data into the processor that some other person who's very intelligent and very sophisticated can infer. That's the idea. And this happens because of the way we design processors today. And this is a perfect example to start this course with, because this gives you the immediate importance of understanding digital design. The way you can understand these vulnerabilities is the only way, in my opinion, to understand these vulnerabilities is by studying digital circuits, digital design. And the only way you can actually fix and protect yourself against these vulnerabilities is, again, by understanding digital design and computer architecture. And this will become more clear in the future. Well, hopefully at the end of these 2 lectures, because we'll go into a little bit more detail over here, but you will not really understand exactly why it happens if you don't understand how a computer executes the programs, and that will happen later toward the end of the course. Okay, what about this one? Has anybody heard of this? Fewer people. Well, you'll learn more, because this is something my research group has discovered. And this is another vulnerability, actually. This is a different type of vulnerability. This exists, we will go into more detail over here, but what happens is in memory chips, these are memory chips. In most memory chips you buy today, you can flip a bit from 1 to 0 or 0 to 1 if you're malicious. Somebody can keep hammering a memory address, and as a result, some other unrelated memory address can flip to a 1 or a 0. So it can actually cause data corruption. And it turns out somebody else can exploit that data corruption to take over your system, to become root on your computer and get any data that they want. So this happens, again, because of the digital design of systems. Why? Because reliability is a problem, and this is a reliability problem, actually. These chips are not perfectly reliable, and there are error mechanisms that can be exploited this way. And these error mechanisms happen to be triggered in a predictable manner. If you keep hammering this row, you can actually cause an error in an adjacent bit. And because of this little bit flip, your entire security, system security, is compromised. Okay? Well, we'll learn more about why this happens. Again, in these 2 lectures, I'll motivate you and I'll give you some examples of why these things happen. Okay. Has anybody heard of these? Multi-core systems. Hopefully everybody here, but most people. But this is essentially what a system looks like today. Actually, this is really old right now. This is a picture that I borrowed from AMD. This is the AMD Barcelona chip from about 2006 or so. But a lot of the systems that we design today look like this. You have multiple processing cores. These are essentially the brains of the system. And they can execute multiple different applications, for example. And you have these caches that store data internally on the processor chip. And you have different controllers that control the memory chip itself. And I didn't show you over here, but then you have connections to the SSD, for example, solid-state drive. And essentially, this thing is inside this little phone, right? And that's what makes it work. And we're going to see how we actually design the cores and how we design the memories. Of course, we're not going to be able to go into everything here, but by the end of this course, you will have a very good understanding of what a core looks like, and actually what a high-performance core looks like. We'll go into advanced techniques like out-of-order execution, speculative execution, but we'll also start with basic techniques like micro-coded engines. So if you've heard of these, but you don't know how this works, this course is about understanding how this works. At least, maybe not all of the system, but most of it, most of the processing core and part of the memory itself. Does that sound good? It's exciting? Yeah. Okay, perfect. I like that. Yeah. Okay, I've given you just 3 examples over here, right? And clearly, if you understand this, you can actually do a lot of things. And by the end of this lecture, we will start talking about what can you do by the understanding you develop over here. So this course is really about hardware, but it's also really not about hardware. In today's world, hardware and software are merging. So I would like you to take this course not as a circuit design course or logic design course, but something that enables you to do bigger things. So a lot of the attacks that we see today are actually hardware level attacks, because software has become strong, even though there are attacks in software too, but hardware level attacks are much harder to prevent. And as you can see, a lot of the security issues going forward will likely be this sort of issues. So when you design software, you'll have to think about these things potentially. Right? And when you design a system, you'll have to think about the entire system going forward. Whether you're making a decision in the future to buy a system or design a system, or whether you're designing software, or whether you're designing hardware, this course will be important for your career. And I think beyond that, I'll give you a little bit more. I think there's an importance to this course that's even beyond computer science. It's really about design and principles and fundamentals. And I'd like to walk you through some puzzles to talk about some of that design principles and fundamentals. Does this sound good? You like puzzles? Okay, let's see how hard these puzzles are first. Maybe they're easy puzzles. Okay. What is this? Well, this is clearly a slide, right? But this is what I meant to ask, actually. How many of you know what this is? Okay, that's good. Not everyone, though. How many of you do not know what this is? That's good. Don't be shy. Not knowing is not bad. Not learning may be bad, sure. Especially if you need that information, but not knowing is not bad. Okay, that's good. Because I didn't know. If I was given this picture, I don't know, let's see, how many years ago? 5 years ago, before I first visited Zurich, I wouldn't know what this is, right? You could tell it looks nice. It looks like an underground thing. So what is it? Can anybody tell me? Yes?
It's the train station in Stadelhofen.
Exactly, yes. It's Bahnhof Stadelhofen, right? Yes. With my terrible German, so excuse my German. It's a train station in Stadelhofen. It looks beautiful, right? I like this. Okay, this is another view of it. Now, have people recognized it? Are there people who still do not know? That's fine. Okay, so you should go there. People who do not know will go there. That's actually going to be an assignment. I'm not going to grade you on it, but it's going to be an assignment for you to actually, I mean, it's for your benefit, basically. In the end, everything you do is for your benefit, right? Grades are not that important. Okay, so basically this is another view of Stadelhofen, which is beautiful. The first time I went there, I think it was in 2015 or so, I was really stunned with the beauty of the station. As you can see, it's built with something in mind, actually. Can anybody say what that is? What does it look like? Does it look like something that you see in other places? Don't be shy. Yeah?
It looks like a Zürich main station, but that's not.
It's Zürich main station, is it?
The Zürich main station.
CERN main station. Where is that?
Lucerne. Well, it's
Lucerne.
city.
Okay, yeah. Okay, we'll get back to that. Maybe there's, I haven't been there, so I don't know. Does it look like something in nature? Maybe it's, yeah.
Looks like a bit like ribs of fish or...
Yeah, exactly. It looks like ribs, some sort of skeleton, right? And actually, this picture doesn't do justice to it because there are more ribs over here. Looks like maybe a bird, I don't know. We'll see. Okay, well, this is another view. There's some fancy stuff over there. It's another view. Another view. I don't know what happened to this picture. Maybe some people wanted to blur these out. They're privacy issues, so you should get used to those also. This is what it used to be. Has anyone seen this? Anyone old enough? No? Again, don't be shy. You can be old. Okay, but this is what it used to be and what it is clearly not today, right? You don't see those ribs. And this is what it used to be even in older times. So it clearly has evolved. And this is 1967, right? And they actually wanted to expand this. They changed the railroad tracks. That's why they wanted to change the station also. And you can read about it. I'm not going to go into the detail. But this is actually similar to what we're going to talk about. A lot of architectures that we design in computing platforms have some resemblance to the architectures that are in real world. They evolve over time. And things that use them also evolve over time. That's why we need new architectures sometimes. Because people use them in different ways, and then they become bottlenecked. They say, oh, we cannot have this station anymore, so we'll have to change it. Right? That's true for computing platforms also, and we've seen evolution of computing platforms. These things were not mainstream 10 years ago. Right? Now they are mainstream. And the internals of it are very different from the past. But fundamentals may remain the same. Okay, let's do some more puzzles. I think a lot of people passed the first puzzle. If you didn't know, that's perfectly fine. Okay, what do the following have in common? What about this one? Has anyone been there? Lisbon? Okay, one person. Just one? One more? Okay, that's good. I've been there recently also. They invited me to give a lecture, and that was the first place I went actually in Lisbon. It was closer to get there from the airport. Okay, keep this in mind. Does it look similar to Stadelhofen? So. Okay. Not so. Okay. This is the internal of Gare d'Oriente. It looks now a little bit more similar, right? You see the ribs. Okay. That's the underneath. That looks very similar. Maybe a not so great picture, but, well, that's what I could find. What about this one? It's in another part of the world. It's the Milwaukee Art Museum. Has anyone been there? No one? I guess I haven't been there also, unfortunately, but I'll have to go now. Yeah, but this is another example, and it looks actually, well, there are some similarities over here. You see there's some principle that's going on somewhere here, right? This is Athens Olympic Stadium. No? I think some people are bored. Why are you showing me all of this? No? Okay. Well, we'll see even more interesting. Maybe you've been here to Valencia. Anybody? You must have been there. Okay, there you go. Yeah, it's closer here. So, yeah, this is actually one of the things that is considered one of the masterpieces Okay, what about this? Okay, I'll do that again. It's pretty fancy, isn't it? No, it's really flying. It's a bird. Oh, it's an animated GIF. I didn't know that. Well, I guess they've become popular recently. Okay, that's another view of that. It's a bigger campus, right? Okay, what about this one? Has anyone been there? Okay, good. Actually, I had a few students from the last digital design course who have emailed me and sent me pictures from the Oculus, because this was one of the assignments, if you will. And they said they appreciated being there. But this is, again, another thing that looks like a bird, right, I assume. Now, there's some information leakage going on in these acknowledgements, so don't read those at the bottom, because that's going to destroy my question, maybe. So, okay, this is my question basically to you. What do all of those that I've shown you have in common with Bahnhof Stadelhofen? Anybody? You don't have to know, you can guess. Yes?
They don't just do the bare minimum in terms of like, they are not just there, but they do something that looks pretty and doesn't really serve any function.
Okay, that's probably true. So basically, what's your name? Andre. So Andre says that they just don't do the bare minimum, but they add something that's pretty but doesn't necessarily serve any function, which may be true. And that's actually, I think they have in common, but you added some commentary in it. For some people, maybe it serves function, right? Who knows? But yeah, that's true. What else? Yes?
They kind of have the same elements, so maybe they're from the same architect.
There you go. That's one. Yeah. Yes?
They all have arches.
They all have arches. Yeah, that's right. They have some principles also. Yeah. Arches, same architect. What else? Yes?
They were designed by Santiago Calatrava.
Perfect. How did you know that?
Well, because I know Santiago Calatrava.
Say it again?
Because I know his buildings. For example, been to the Oculus and also to
Okay, there you go. He knew about it, and he has basically that's the answer I'm looking for, but all of these are, I think, correct answers. You didn't know the architect, clearly, but you know that you guessed that they were designed by an architect. Yes, they were designed by the same architect, basically. A famous architect. How many of you know Santiago Calatrava? Okay, apparently he's not famous enough for this audience. But you should know him, because he's an ETH alumnus in civil engineering. And that's actually the reason he designed Stadelhofen. That was his first real big job, if you will. And as you can see, this is some commentary from Wikipedia. The train station has several of the features that became signatures of his work. Straight lines and right angles are rare. And we'll look more into this. Yeah. Yeah, as you can see, Milwaukee Art Museum is actually one of the highest ranking buildings actually, that's one of the masterpieces of modern architecture also. Okay. Okay, I'll give you your first digital design assignment, although I've already given you that, I think. Please go and visit Stadelhofen, especially after a few lectures over here, and repeat for any Calatrava building. It could take some time, but then you'll also get exposed to many parts of the world. I told you it'll be fun to take this course. You can appreciate the beauty and out-of-the-box and creative thinking, or you can say that this is useless. That's also perfectly fine. No problem. I mean, this is also art, right? It's judgmental in the end. So okay, I'll make another point, even though I didn't intend to over here. Everything we see in the world is heterogeneous. We have heterogeneity among us. We have heterogeneity among everything we see in the world. We have heterogeneity in opinion also, and we have heterogeneity in the system also, and we will see that. This thing doesn't have just the component that I've shown you. It actually has, I don't know the number actually, but I'm going to make a wild guess, at least 10 different accelerators, 10 different types of processors inside it. Some of them are doing video decoding, video encoding, and they're very specialized for doing that. Some of them are doing graphics processing, not video decoding and encoding, graphics processing, like displaying stuff on the screen. They're specialized for that. Some of them are doing the multi-core processing. Some of them are smaller, low power, low performance. Some of them are larger, high power, high performance, and they're vulnerable to spectra and meltdown. Maybe the smaller ones are not vulnerable because they don't execute things speculatively as much. Right? So there's heterogeneity in everything we design, and there's heterogeneity in the nature also. Okay, so think about the trade-offs in the design of the Bahnhof. Think about strengths, weaknesses, goals of the design. I think it's always good to think about those, because these are actually what we will talk about in this course, after covering some basics, real basics. So this course is really about understanding the goals of a modern microprocessor platform in general, and the strengths and weaknesses of different ways of designing it, potentially. And you can derive your principles on your own for good design and innovation if you think deeply enough about the Bahnhof, I think. Well, due date is anytime during the course or after the course. I've gotten, I think, emails from past students this summer with pictures of the Oculus in New York, which we will talk a little bit more about. And later during the course is better because you will actually hopefully get into the mindset of evaluating things in a trade-off based way. Especially the second end of the course will be like that, because we will cover a lot of processing paradigms in computer architecture, most of which are employed in, actually, I think all of which are employed in existing systems today. But they're employed in different things. Like multi-core system, the simple processor is not the only thing that you see. Okay, you can apply what you've learned in this course, and maybe you can think out of the box. Because we need actually creative thinkers in this world to make the world a much better place. And I think thinking about computer architecture that way is a very good way of doing it. But first, let's do today's first assignment. And another puzzle for you. I think this actually will goes well with your comment earlier. I'll ask, find the differences of this and that. So of course, for this, I'll have to give you this and that. So this is this. You already figured out what this is. It's Bahnhof Stadelofen. And this is that. I don't know what this is actually, but it's clearly a train station. Maybe this is what you would call bare minimum. I'm not sure if it's bare minimum. It's still pretty good, right? Looks nice. It's functional. But it's clearly not this. So which one do you like better? Now we'll see the heterogeneity, probably. Who likes this one more? Okay, quite a few. Who likes this one? Okay. There's some number of people, that's good. So why do you like this one better? Anyone who voted for it? Yes. You have to, I see, you're bored of the other one, I see. So you want to see something different. Maybe it's out in the, well, the other is out in the open also, but maybe this is a different field. Exactly, yeah. Maybe you overuse it. It's worn out on you, right? Actually, computers become worn out also. Memories become worn out. So you actually change them. Okay. So you can list them after you complete the first assignment, of course. But I think the point I want to make over here is it's not really clear what's better, because when I actually asked you which one do you like more, you make a judgment call, right? And it was a quick judgment call. What metric did you use? Probably a general metric that your brain gave you, saying that, oh, this looks good to me, right? But when we evaluate something, maybe we do it more rigorously, right? Basically, if I actually have to evaluate these two designs, I would like to come up with some evaluation criteria for the designs, right? Because these things were perhaps designed with different goals in mind. So functionality, does it meet the specification? Is it reliable? Space requirement, cost. Well, I can tell you that this costs a whole lot less than this one. Actually, Calatrava was criticized quite a bit because of the cost of Stadelofen, and we'll talk about the cost of Oculus later on. How many of you know the cost of Oculus in New York? Any New Yorkers here? Well, Zürich, New York is a relatively short flight, actually. Okay, we'll get back to that. But basically, expandability, can you expand it? Comfort level of the user, happiness level. Maybe you voted based on the happiness level, I don't know. You'll have to think about that. The psychology experiments are that way, right? They usually measure something. I don't know what I was measuring over here, but aesthetics, maybe you voted based on that. Security? Which one is more secure? I don't know. But I'll give you some examples later on. Security actually dictates the design choice in these things also, not only in computing platforms. And ... I mean, there are many, many other things you could come up with. Energy efficiency, for example, which I didn't put over here. So there are many, many criteria for the designs. And your design goal is also based on, you design something based on some goal also. So we'll talk about that. Basically, how to evaluate the goodness of a design is always a critical question. So performance evaluation and what metrics you develop will be important. And you will see some metrics over this course on measuring microprocessor performance. But it's not just about performance, it's about reliability, security, energy efficiency, ... Especially with the systems that we design today, there is no single performance metric. Keep that in mind. And I said performance because performance is not just about how fast it is, how long it takes to execute a program, for example. It's also about how much energy you consume. How reliable are you? How secure are you? Maybe you don't care about how fast you are if you're not secure, right? If somebody can take over your system right away. So keep thinking about this. This is not rigorous at the moment, but we'll put some rigor into it later during the course. So a key question that I will ask, changing the topic a little bit, how was Calatrava able to design especially his key buildings? Any guesses? I'll have a laundry list over here soon. But what do you think was the key element? No? Creativity? Yes?
Maybe new inspiration from nature.
There you go. So some principle, basically, right? Yeah, exactly. That'll be one of my ending points over here. I mean, clearly you can have many guesses, and it's probably a combination of many, many of those, right? Because you may have principles from nature, but then if you go and slack off and do nothing, then those principles are useless. So he probably put a lot of hard work and perseverance and dedication over decades. He developed that experience, creativity. He probably thought differently from some others. Probably he had a good understanding of past designs. I mean, I'm not claiming that this is true, but these are actually good things that you should have that can actually all enable you to build better systems into the future. And this architecture is just one example over here. Maybe good judgment and intuition, right? That's actually important. It's good to develop that based on the past designs. Strong skill combination, math, architecture, art, engineering, or at least figuring out how to enable many people who have the combination of those skills together, right? Funding. We'll see that that's also important in this. Luck, initiative, maybe entrepreneurialism, and strong understanding and commitment to fundamentals. I think we'll focus a lot on that in this course. I'm not going to be able to give you funding, sorry. Who knows, maybe. If you have a really good idea for a startup, we can talk. But yeah, maybe not $4 billion, please. Okay, principle design. And you will be exposed and hopefully develop and enhance many of these skills in this course. Yeah. And keep this in mind. I think whenever you think about an idea that we will discuss, especially toward the later end of the course, in initial parts, we'll need to build some basics so that you can actually think about a microprocessor. But especially toward the end of the course, you will need to maybe think about the different advantages and the disadvantages of the designs. And it's always good to think about what kind of skills you need to enable such designs. So we'll especially focus on principled design and a strong understanding of and commitment to fundamentals, because I think this is really, really important. And that's what such a basic course is about, giving you the principles and the fundamentals. Okay, principled design. I think we've talked about this, but let's see this in the words of Calatrava. He says, "To me, there are two overriding principles to be found in nature which are most appropriate for building. One is the optimal use of material, maybe not so well defined, but think about it, it's very efficient. And the other, the capacity of organisms to change shape, to grow, and to move." Maybe that's why he's fascinated with these ribs, right? Because that's what really enables those movements. And other people have said Calatrava's constructions are inspired by natural forms like plants, bird wings, and the human body. And this is, we go back to the Gare d'Oriente in Lisbon. What do you think these things are? Anybody? Looks like what? Turtle. Yeah, that could be actually. Yeah? That's good. I like the creativity. This is in his drawings. I guess people who are holding the thing. Okay, now it looks more like those probably, right? Once I overlaid this on top of that. But this gives you one of the principles, right? Okay. So the principle is really zoomorphic architecture. It's the practice of using animal forms as the inspirational basis and blueprint for architectural design. And you can go and read more about it. I'm not going to test you on zoomorphic architecture in this course, but it's always good to know different fields because this really enables you to do better things in life in general. Okay. And as you can see, some well-known examples. There are many other ones. Okay, let's go back to the Oculus. What does this remind you of? That's a bird, I think. That's what I heard, right? Anybody else think this is a bird? Raise your hand if this is a bird. If you think this is a bird. Anybody else thinks something else? Which is perfectly fine, yes?
Manta ray or something like that.
Manta ray. Oh, I've never thought of that way. But yeah, I could see it being that way. The internals, yeah. I mean, it's the internals of a bird also. What else? It can be a good art critique, maybe. Or architecture critique. Okay, yeah, you have?
I think a Venus flytrap. I just think of that. A Venus flytrap.
Oh, flytrap, okay. Yeah, I say, okay, yeah, that's good. I like the creativity. Keep it coming. Okay, well, actually, he wanted these things to move. So you're right, it would have looked even more like that. But he didn't have, people ran out of money. They didn't move in the end. It was not the Florida Polytechnic University. I don't know where they were funded from. But okay, basically, Calatrava said the Oculus resembles a bird being released from a child's hand. So clearly there's a blueprint over here. The roof was originally designed to mechanically open to increase light and ventilation to the enclosed space, blah, blah. Okay, you can read more. you can read it if you want. But clearly there's some strengths to this design, and it has gotten praise. For example, somebody publicly said, it's a pleasure to report for once that public officials are not overstating the case when they describe a design as breathtaking. So that's a clear praise, right? But he was subject to design constraints and criticism as well. And I'm showing you this because this is going to be true for architectures that we design also, platforms we design, or any design you will be involved in. Let's take a look at one of the design constraints. And it will go back to something similar to Meltdown and Spectre. So this is criticism and the design constraint at the same time. In the name of security, Santiago Calatrava's bird has grown a beak. Its ribs have doubled in number and its wings have lost their interstices of glass. The main transit hall, blah, blah, will almost certainly lose some of its delicate quality while gaining structural expressiveness. It may now evoke a slender stegosaurus more than it does a bird. Does anybody know what that is? Slender stegosaurus? You played with those before, right? Well, it looks like this. I didn't know what this is before I read that comment, actually, but it looks like a dinosaur. So clearly, this is not a praise for the architecture. Well, unless you're happy with the dinosaurs. Okay, so, but clearly, actually, you need to read more about it, but security was a first-class constraint in the design over here, and that dictated some of the design choices he had to make in order to design this building. He couldn't make some of these things longer. He couldn't make, because this is actually situated in the middle of New York, at a very, very crowded area. So clearly your design constraint is dictated by whatever else is around you as well, which is similar to what we do in computing platforms too. Okay. As you can see, the design was further modified in 2008 to eliminate the opening and closing roof mechanism because of budget and space constraints. Now, other design constraints kick in, not only security, but budget, cost. That's always a design constraint. And I'll give you an example. There used to be people, I don't know if they still exist, I'm sure they still exist, but they said they were building these huge supercomputers. Mainly for the US government, for whatever reason. Maybe not so good reasons, but basically they said cost is not a concern for us. Well, maybe I'll leave it at that, but cost is always a concern. You don't have infinite money, and an engineer is someone who would do for a dime what any fool can do for $1. This is what someone said in the past, and that's true in every design. If you can do the same thing for a dime as opposed to $1, your design is better. I said the same thing, right? And cost, you need to incorporate cost into your design all the time. Of course, the amount of cost depends on the budget that you get and what you're trying to achieve, but never forget that cost is a concern in design. Space constraints, that's also a concern in computing architecture. You don't have a lot of space here. You may have a lot of space in a data center, right? You may actually design a huge computer over there. But here, you're very much limited by energy and space. So you would like to minimize things as much as possible. And that's a very similar constraint in Calatrava's building. It's in the middle of New York over there. You should really go and see it. Okay, well, regardless, even then, the transportation hub has been dubbed the world's most expensive transportation hub, very close to $4 billion. So that's what it cost the New Yorkers. It's nice, though. Okay, so you could argue that's a good idea or a bad idea, but it's there. If it's there, you should go and visit it and get inspiration and evaluate it. Okay, let's do the same puzzle with a different example. Does anybody know what this is? Okay, some people in the back. Okay, who does not know what this is? Don't be shy. Okay, I wouldn't have known what this is if life didn't bring me to a place that I lived for a while. So who would guess what this is? Yes?
This is falling water house.
Falling water house, perfect, yes. It's falling water, essentially. Where is it?
I think it's somewhere in the US, but I'm not.
That's good, that's good. So you have not been there, basically. Okay, you know about it, but you have not been there. That's good, so it's famous, as you can see. Okay, so it looks nice, right? It's actually built on a waterfall. This is a waterfall, and the building was built on top of it. And this is another view. As you can see, it's very much harmonious with the nature. These cantilevers over here are supposed to imitate the waterfall. You have a big one over here that's imitating this one. You have a small one over here that's imitating this one over here. And there are a lot more other elements over here. This is yet another view. And, well, it's also the masterpiece of another famous architect. Now you know the other puzzle. Who's that architect? Perfect. Are you from the US? No. Okay. Have you been there? No. Okay. How do you know that?
I wrote several presentations about it in school.
Okay, that's good. So knowledge is good. Did anybody else know about this? Yes. Okay, cool. That's good. So this is the other architect. And as you can see, you can read about it. It was really, this is actually one of the things that are taught in Architecture 101 classes. I don't know who compiles these lists, but apparently you must visit it before you die. And it's only one of the 28 places. So you should probably take a look at the other 27 also. Of course, it's subjective, right? Okay, we'll get back to this a little bit. So let's take a look. So this is the design. I think this picture does not do justice to it, but I wanted to put it in comparison to that. It's actually, I would say this is a regular American architecture building in the rural environment. And this is probably not so regular, right? So you can see, I mean, I'm not going to ask you the question again, but there is a difference between this and that. And there are many, many trade-offs between them also, right? And I'll ask the same question. I was right able to design his masterpiece, and I'll give you the same laundry list of items over here. So, but clearly what he had was principled design, and he was also very committed to the fundamentals of it. In fact, these two architects are probably very similar in the sense they were committed to the fundamentals of design. Right, a little bit, maybe more so actually. He said architecture should be based upon principle and not precedent. And if you actually, precedent meaning something that comes before, right? If you actually design things based on the precedent, then he could have designed this. And then he wouldn't have been Frank Lloyd Wright. You wouldn't have known about him, right? Or read about him. But he instead designed this, which is clearly a much more principled design. Now, you could argue that this is also principled, right? There are different principles over here, clearly at play. So I'm not suggesting that the precedent doesn't have principles, but if you want to move things forward, you cannot stick to the principles that the precedent is just based on. You really need to have principles that are dictated by the constraints of the design and the goals you have in life. I'll give you an example with Meltdown and Spectre. The precedent was designing things to be very, very high performance. Maybe that's good, and maybe we should keep doing that, but we have these security problems. Then what do? Maybe you should rethink some of the principles that you have, such that you can actually design a system that's both secure as well as high performance. That's why it's always good to know what the precedents are and what the principles should be for you to achieve your goals in the design. And we will talk a lot about that in different contexts in this course. Okay, so what's the principle here? Anybody guesses? The principle of Frank Lloyd Wright? Yes?
Maybe try to make sure that the house harmonizes with nature.
Yes, that's right. That's exactly it, actually. It's called organic architecture. It's a philosophy of architecture which promotes harmony between human habitation and the natural world through design approaches so sympathetic and well integrated with its site that buildings, furnishings, and surroundings become part of a unified, interrelated composition. And as you can see, the well-known example is Falling Water. This is actually in rural Pennsylvania. It's very close to Pittsburgh. That's why I've been there many, many times. I used to be at Carnegie Mellon University before coming here 2 years ago. And I like talking about this because this is a place that's close to my heart, and Stadelhofen is a place that's even closer to my body right now, I think. Okay, so I think it's a beautiful picture, as you can see. Maybe I should have put some of the pictures that I've taken. Okay, so principled design and strong understanding of and commitment to fundamentals. That's what this course will be a lot about. Okay, let's go back to Stadelhofen and have some more fun over here. So architecture evolves, as I said. This is what it is today, actually circa when the picture is taken. 1967, it was something like this. 1968, it was something like this. It's similar. And it transformed, right? They gave the job to Calatrava, and he turned into building. As you can see, building happens based on some basic materials. It's not magic, but you use some technology to build an architecture. And you use some other technology, different parts. It's heterogeneous, as you can see, right? You don't build everything on wood here, but there are wood parts also. And it transformed over time, and it became this. That's the end result. So the end result is what you see. Of course, the end result is what you see over here. But understanding how you get to that end result is really critical so that you can actually build things that are better than this, for example. Okay, so takeaways. Why am I showing you all of this again? Basically, it all starts from the basic building blocks and the design principles. Something happened here. Okay. And the knowledge of how to use and apply them, right? This is really critical. That's true for computer design. That's true for building design. That's true for any design. And I'll say this is going to be really, really important. Underlying technology might change. It could be steel, it could be wood. I don't know, it could be, in computers, it could be, electromechanical designs. It could be some type of memory versus some other type of memory. But the methods of taking advantage of technology bear resemblance. And this is the really fundamental part. You need to understand how you can take advantage of this technology, or any technology, if you will. And methods used for designs depend on the principles that you employ. Clearly, Santiago Calatrava employed some principles, and he used methods to enable those principles, right? Okay, this is actually a good place to take a break, because we're going to jump into the same thing as applied to processor chips, and we're going to have some more fun. let's take a break for 15 minutes. Okay, let's continue. Okay, we'll continue where we left off, but before that, a lot of you asked me about exercise sessions, when you will be able to sign up. Juan will send an email later today. Juan is the head TA over here with Hassan over there, so there are two heads, as you can see. But he will send an email soon about that, so don't worry. And next week, we will have a single session dedicated to labs and exercises and the FPGA boards led by Hassan. So you will learn a lot about that next week. Okay? And if you have any questions, we will give you the email address for the course so that you can reach everybody together. But I'll do that tomorrow because I wanted to have fun today. Is that okay? Okay, yes, I heard a strong yes, so I didn't hear a strong no. I guess nobody wants to not have fun. Okay. So let's continue the fun then. So basically, these were the takeaways, right? This is essentially what we were trying to achieve with this course. This is a fundamental course. It's one of the first courses you're taking, one of the required courses. So you need to be exposed to basic building blocks and design principles, knowledge of how to use and apply them, and understand that underlying technology might change, but methods of taking advantage of technology bear resemblance, and you can actually use those methods depending on the principles that we're employing. And I'll give you examples of this. I may give you an example very soon, but especially when we go back. Well, I'll give you one example. For example, at Carnegie Mellon, I used to teach this architecture called systolic arrays. Has anybody heard of systolic arrays? You've heard of it? Anybody else? Okay, one more person. What is a systolic array? As you know it. It may be. You've heard of it? Okay, you don't know what it is. Do you know what it is? Well, systolic is related to the heart, right? You guys know about this? Basically, heart pumps blood. And this is actually an architecture that's based on the heart pumping blood and blood circulating in the different cells and cells operating based on that blood. And the idea is the heart doesn't pump blood to every single cell differently, right? The heart pumps blood to some interconnected set of cells, and the blood goes around and circulates, and the cells operate using that blood, and it goes back to the heart, right? So this is essentially a systolic array, actually. And the person who invented it, H.T. Kung, when he was at Carnegie Mellon at that time, he basically said computers should be designed this way. Because it makes no sense the way we're designing computer today. Every time the computer needs blood, the processing element, a cell needs blood, it gets it directly from the heart and then puts it back. That's not how the body works, right? The body works by getting some blood and circulating it such that a lot of different cells operate on pieces of that blood. So that's a systolic array at a high level, motivated by nature. Well, I used to teach this architecture, and there were no real examples of this architecture, let's say when I was teaching 9 years ago. But it was such a fundamental thing to teach. It was so important, in my opinion, because it had a very big principle. The principle is you don't go to the heart every time, or heart doesn't go to you to actually do the processing in the cell. It's really an interconnected set of elements. And the data, if you will, the blood flows through those interconnected set of elements. Every single element does some operation on that data, and the data transforms as it flows, and it goes back to memory, which is the heart. And then you keep doing this. So this saves a lot of data bandwidth, or blood bandwidth. As a result, you're much more efficient. Well, come 2016, 2017, this architecture is employed in Google's tensor processing unit, because they figured out that this is one of the most efficient ways of accelerating machine learning workloads that they have in their data centers. As opposed to going to the memory every single time, you basically bring in inputs from both sides. It's a two-dimensional array in this case, not the one-dimensional cells that I mentioned. You bring the inputs from here, X inputs, and then Y inputs here, and the data flows. You do the calculations, and you pull the data out after that. So this architecture is real now because it is based on a very solid principle. The principle is saving memory bandwidth, similar to what all those other architects have done, right? They were inspired by nature. And H.T. Kung, if you read his 1982 paper called Why Systolic Architectures, he says exactly the same thing. I'm inspired by the heart. So this is, if we will talk about it when we get toward the end of the course, because we need to build up to it. But toward the end of the course, we will talk about systolic arrays, and you will see that this is an architecture that's revived and that's employed basically pretty much in all of Google's data center computers today, and it's probably mining some of the data you input over there right now. Because it's doing machine learning on big data, right? And big data is collected everywhere in the world. Okay. That's an aside, and it's clearly not here, but it will come in soon. So this is actually a slide. So basically, the principles apply to processor chips also. It applies to memories as well. We will talk about that. But I wanted to give you some chips over here. This is a slide that I made a long time ago, maybe 2008 or so. So you may actually not know what some of these processors are, but Intel Core architecture is still around. NVIDIA has much bigger chips right now. As you can see, these actually are built based on some basic building blocks and design principles. The cores themselves, the caches themselves, the memory controllers, the interconnect among them, they're all based on some principles. As you can see, there's some principle over here, which is really replicating the cores. That's the idea of multi-core engines. You can see that you replicate the cores, you form a cluster, and you form another cluster over here. So that's a hierarchical design. That's one of the principles that you can see. Intel Cell broadband engine. This was employed in Sony PlayStation. And this is one of the first heterogeneous chips that were designed. Basically, you have this powerful chip, and you have these 8 different other chips. So one powerful chip and 8 different other chips. One powerful processor and 8 different other processors. You have a question?
In the Intel Core 7, I only see 6 cores.
Well, and this is old, probably.
Okay.
Yeah, this is not today's, yeah. Think 2008 or so, whatever, okay? Don't take these as the state-of-the-art chips, but this is an example. And state-of-the-art is similar, but yeah, maybe it has right now 24 cores or something like that, maybe, I don't know. So I may not know, but I know the principles, that's the good part. Okay, so Power 7 is one of the earlier chips, not the earliest multi-core chips. Power 4 was on one of the earliest multi-core chips. So it has similar design principles. You can see the hierarchy, right? Over here, if you look internally. 4 cores over here, 4 cores over here. They're somehow hierarchically designed. Some of them share caches, some of them don't share caches. If you don't know about caches, you will see soon. Sun Niagara, this is actually one of the, Niagara 1 was one of the earlier multi-core chips also. I don't know why this picture is so weird here, but anyway, it doesn't matter for our purposes at this moment. So NVIDIA actually, that's another type of chip, graphics processing units, which we will cover. You will get exposed to the fundamentals of, because you have to. At this point in time, a computer architecture course, a digital design course, has to cover these chips also, because these are so dominant in the field. Actually, NVIDIA is right now doing a lot of machine learning because of the processing power that's possible in these chips. As you can see, there are 448 cores, but there's a different definition of cores, and we will talk about that when we get to it. But there's a lot of processing power inside these chips, and you will see the principle of it. The principle of this is very different from the principle of this, even though it may look like the same, right, in the end. There are some principles that are shared, like hierarchy, regular design, but how you actually exploit parallelism is very different here. So this exploits something called a single instruction multiple data parallelism. You can give a single instruction that can operate on 1 million data elements. That's exploited in a very limited manner over here. That's fundamentally not how this is designed. But this is very different. Okay, I'm not going to go through all of these, but I'll point out one other thing over here. So these are actually based on these are essentially distributed systems on a chip. Basically, you have these cores, in this case 48 cores, in this case 100 cores, and they're connected to each other via a network. And network is very regular, as you can see from the structure. And there are routers in each core. So if one core needs to communicate with some other core, it goes through a router. So just like the internet is that way, right? In internet, whenever I type something over here, it goes through the network somewhere else. This is a network on a chip. And these things exist. So you can see the complexity of the designs that we have today. Because of Moore's law, which enables us to put more transistors on a chip, essentially technology, fundamental technology, we know how to manufacture many devices on a single chip. As a result, we can add more stuff. We can make these chips much more capable. And we will talk more about that in the next lecture. Okay, so hopefully this gives you an idea. This is clearly not the entire space. There are many other types of chips. And I didn't even put the specialized chips. So for example, I'll talk about this one. Sun Niagara actually has a cryptographic engine inside it, a dedicated processor, one of these that you cannot see and I cannot see. But one of them is a cryptographic engine. It basically encrypts and decrypts packets that are coming into the chip. All of its function is that. Well, why do you do that? Because it's specialized for that task. If you specialize it, it can be much more energy efficient and much higher performance. And if you're receiving packets at 100 gigabits per second, let's say, you can process it as fast. Whereas if you actually take those packets and try to encrypt and decrypt them in a core that looks like this, that's not specialized, that's very general purpose, it takes much more energy and it may not even meet your bandwidth requirements, which is 100 gigabits per second. Right? So basically they put a cryptographic engine over here that processes packets in a very specialized manner. So this is another principle, specialization versus general purpose, right? Specialization always makes things much more efficient and much more higher performance if you design it well, of course. But it comes at the cost of doing that thing only, almost, right? You cannot, this cryptographic engine cannot run, I don't know, a virus checker, for example, because it's not designed for that. It's designed to only do encoding and decoding, cryptographic encoding and decoding. There's also a video encoder and decoder inside here. It cannot do cryptographic encoding and decoding, perhaps, unless you transform the problem there, but it can do video. It can do very fast MPEG decoding, let's say, or MPEG encoding. Okay? So these chips have actually many components in them, and we'll cover some of these principles. But one of them you should keep in mind is specialization versus general purpose. We'll talk a lot about the general purpose design in this course. We'll talk about other paradigms also, like graphics, SIMD units, single instruction, multiple data units. And also we will talk about systolic arrays, things like that. We won't be able to cover the entire spectrum because the spectrum is actually really large. And if you go to, even if you go to a company that traditionally doesn't design these things, you may actually be exposed to them because all of these large-scale companies, Google, Microsoft, are actually going into the design of these chips because they're figuring out that you really need to accelerate the computations they have. Machine learning is a really good example. These computations are so data-intensive that you have to design your specific chips or carefully designed chips such that you can actually make things much more efficient and faster. Okay, so let me give you a very quick overview of the different design spaces. Basically, there are basic building blocks and design principles that apply to all of these, but there are also some things that distinguish them. So this one is a data center example. You see many chips. You don't know what's inside them, but the principles of the underlying computation units are actually similar. There's another thing. How many of you have played with this? Oh, that's quite a few people. That's good. So you played with drones. So you can see that it's a different platform. It clearly has a different goal, right? It clearly has a different design constraint. Now, I wish I had a picture of something that I put into my head and that enables me to process whatever comes up from here. That is clearly a very different design requirement and design goal, right? You cannot put something extremely power hungry onto your head because you may burn your head. Nobody wants that, I think. Right? So your design is really dictated by where you're going to use it. And clearly this is a very different design requirement. So another one. Have you driven a self-driving car like this? Well, actually, clearly this is a different design constraint, right? And if you really want to drive it this way, you'd better have a very stringent security and safety constraint over here. But clearly these self-driving cars have different design constraints. So this is another example. This is, I think, an earlier version of the Google self-driving car. You can see that there's a huge computational thing over here. So when I was at CMU was actually participating in these huge challenges that were huge competitions, basically, that were sponsored by the Defense Agency in the United States. And one of the goals was the self-driving car challenge. And if you looked at, I wish I had a picture of that also, but you can find it online. If you looked at the back of that car, it essentially was a mini data center. To be able to enable that car to self-drive and do all of the vision processing, do all of the learning that it needs to do to avoid all of these traps, if you will, and ensure that it drives well, you needed a mini data center over here. Well, today we've come a long way. That was circa 2007, 2008. Today, these are actually much more efficient. So clearly, you don't want the data center in your car because otherwise it won't be your car. What else are you going to put there if you have a data center driving it? Okay, so think about that. This is a supercomputer. This is actually, I think it's still the top supercomputer in the world, Tianhe 2 in China, although it's going to be surpassed probably. There's intense competition between these supercomputers. These are actually the largest computers that you can see in the world today. But these are also built based on similar principles, but the goals are different. Here, maybe cost is less of a concern, right? Where here, cost may be a huge concern, right? But even then, as I said, cost is always a concern. For example, these supercomputers are evaluated based on their energy efficiency. It used to be the main metric was flops. Flops meaning floating point operations per second. How many billions of it can you have? Today, it's not like that. Today, people are evaluating these computers in terms of flops per watt. How efficient are you in actually when you're doing computation? Right? That's another metric. Maybe security should go into it with its own metric, right? So think about that. Clearly, we have many different platforms with different goals, but the fundamental principles are similar. So this is actually what I said earlier. This is the systolic array. You can see the systolic data flow word from Google's paper in 2017. Basically, this is another platform. This is, in fact, the earlier version of this, what they call the TPU, Tensor Processing Unit. And we will see this operation later on, but the principles are similar. Okay, so let's talk about these basic building blocks for the rest of the time we have. Clearly, we need to start with something, and usually we start with electrons, but we're not going to talk much about them. You can take a physics class to talk about them. They're fun. And you build up to transistors, logic gates, combinational logic circuits, sequential logic circuits, storage elements and memory, ... cores, caches, interconnect memories. So we're going to cover a lot of that in this course, actually. We're going to start very quickly with transistors and then talk about these, and then come to this area, although we're not going to cover everything over here because it's a huge area. The next course is really the computer architecture course after this that continues what we covered. So you're going to learn a lot about these basic building blocks because they're so important. You don't need to know exactly how electrons work for this course. We'll abstract everything based on at the transistor level. Transistor is a switch. It's on or off, and electrons enable that on or off behavior. Okay, and everything will be built upon that. Okay, so you will have reading assignments. I wanted to give this to you. I know we are having fun, but this is also fun, hopefully. Yeah. Please try to do the readings. That will enable you to understand the lectures a lot more. I'll try to give the readings earlier than the lectures. And we have two books because they're very different. Remember I said everything is heterogeneous? Teaching styles and learning styles are also heterogeneous. And I would recommend you to follow both of the books. At some point, we're not going to cover everything over here, but that's also true here. So you should read chapter 1 in this Harris and Harris book and chapters 1 and 2 in this Patz and Patel book. And there are supplementary lecture slides on binary numbers. I don't want to teach you binary numbers because I think it may be insulting. You guys know about binary numbers, right? How many of you know about binary numbers, binary representation? How many of you don't know? Don't be shy, again. No problem, binary numbers. 1, 0. Okay, if you don't know, and if you're shy, that's okay. You can go and read the supplementary lecture slides, so I think I feel justified in my choice of not teaching you binary numbers. Thank you. Because there used to be, I think it used to be taught, and I don't think you need to learn about binary numbers in a 1.5-hour lecture. Okay, so let's talk about the major high-level goals of this course. In digital circuits and computer architecture, I'd like you to understand the basics, principles of design, and the precedents. Precedents are important. Systolic array was a precedent 10 years ago. Now it's real. It's again back, right? Based on such understanding, you will learn how a modern computer works underneath, evaluate the trade-offs of different designs and ideas, implement a principled design as simple, very, very simple microprocessor. If you want to do more, feel free, but you should cover the basics. If you want to do even more, you should really take the computer architecture course. And learn to systematically debug increasingly complex systems. So debugging will be an important part of your labs, for example. And hopefully, all of this learning will enable you to develop novel out-of-the-box designs. Now, this is not going to be a requirement of this course, but this will be hopefully all of this will enable you to do this. Because in the end, what really makes the world progress is the productivity, right? The new things that you can generate. Especially at an elite school like ETH, that's our goal. Right? You're the leaders of the future. Okay. So the focus is on basics, principles, precedents, and how to use them to create and implement good designs. So let's take a look at, so why these goals? Any question? Or no? Okay. So why these goals? Well, because you're here for a computer science degree, and computer science is very broad today. And I think computer science, as a computer scientist, you should really know how to design systems. But hopefully this is not the only reason. Because regardless of your future direction, learning the principles of digital design and computer architecture actually will be useful to design better hardware, if that's what you would like to do in the future, and you may not know what you would like to do. That's all the more reason to learn these things. Design better software, and I'll give you some more examples of this in a little bit, because if you understand what's going on underneath, you can design much better software. That's exactly why companies like Google are doing tensor processing units today. They're designing hardware so that their software runs much faster and much more efficiently. And they're going through all the pains to design the entire system around that. Design better systems, again, that's the reason why these companies are doing that. So it's not just, so if you actually look at the spectrum, the companies that are doing digital design are not limited to Intel or NVIDIA or AMD or IBM. It's really very, very broad today. Apple certainly is doing it. ARM is a company like that, but Google, Microsoft, Facebook, all of them are actually, all of these big internet companies are doing it. And you can do it also. Okay, make better trade-offs as design. I think this is really fundamental to everything that we design in the world, not just computing, everything else, as we've seen earlier. Understand why computers behave the way they do. I think this is actually a really, really challenging task. I cannot know why something behaves they do because I do not have enough information, right? Even though I know the principles, you really need to know a way of getting to that, exercising those principles. Solve problems better and think in parallel. So keep this in mind. A lot of the processing systems that we have today are very parallel. So starting to think about how to actually do computation in parallel is really important. And if you start with a hardware design, and if you see the parallelism in hardware, hopefully this will enable you to think much more in parallel. Because if you look at the hardware design itself, it's very parallel. There's nothing more parallel than hardware because the signals are going everywhere in the same cycle, right? And you need to somehow make sense out of that parallelism and ensure that you coordinate it. So this is going to be really, really important, especially in the labs, but also in the conceptual things that we discuss in the lectures. And if nothing else, hopefully you'll learn to think critically because this is really, really important. So you should really think critically, especially toward the later parts of the course where we talk about different processing paradigms. Okay, maybe there's ... also. Did I convince you that this is good? Okay. Some people are bored, but that's good. Well, okay, let's go to some even more boring stuff. I'll ask you this question. Why do we have computers? Does anybody have an answer? We should start with that question, right? Because the alternative is not having computers. I'm not talking about this course. Yes?
Problems that we will not have without them.
Okay, we will not have without them. Okay, I don't know about the we will not have without them part, but to solve problems I like, yes.
Yeah, to solve problems that we are too late to solve ourselves.
Okay, that's good. So I think actually, probably that's the reason we have computers, but then there are some other problems that come because we design computers. So you have some fundamental problems that you want to solve, and you have some additional problems that you need to solve because you've designed these computers, right? So why do we do computing? It's the same question. Basically, the answer is to solve problems. So let me reword that answer, to gain insight. This is actually what Richard Hamming said in his seminal paper. The purpose of computing is really to gain insight. Because solve problems, you need to solve problems to gain some insight. And you need to gain insight to enable a better life and future, right? That's really the goal. Otherwise, we don't need to have computing. But of course, as you indicated implicitly, the design creates some other problems that we need to solve to maintain this probably, right? Security is one example of that. Okay, how does a computer solve problems? Any guesses at this? Maybe it's too general of a question, yes?
By using a program we wrote ourselves. I mean, the computer is not going to be able to solve the problem by itself. We have to explain it how to.
That's right, yes, exactly. At least that's how I like to think also. But with artificial intelligence and machine learning, maybe it's going to solve its own problems also, right? Anyway, yes, I get your point. So I think that's one, you've jumped through a higher abstraction level. I'll start with a much lower abstraction level. It solves problems by orchestrating the electrons. That's the lowest abstraction level I'd like to start with. Of course, at least in today's dominant technologies, right? This may not be true if you have a completely mechanical thing. But in the end, those are also composed of electrons somehow. But okay, anyway. So how do problems get solved by electrons? Now we need to build the abstraction level that you said. And that's what brings us to transformation hierarchy. So you start with a problem. I have a problem, and I need to solve it. And I have some electrons that are sitting around who want to do jobs for me. But I don't know how to communicate with them, right? I somehow need some communication channel. Clearly, I cannot speak in electron language. Maybe some of you guys can, or girls can. And they don't speak my language. I've never communicated with them. So we need an abstraction level. And that abstraction level is the transformation hierarchy. Basically, the problem gets transformed to an algorithm that gets transformed into a program in some language. And that language gets translated and executed. It goes through some system software, although this is not exactly like this, but that's okay. And then it eventually gets translated to the software-hardware interface. This is called the instruction set architecture. We'll distinguish between that. And then it gets, instructions get executed in the microarchitecture, and the logic gates enable those, and logic gates are built of devices, and devices operate based on electrical principles. So this is the transformation hierarchy. And this is what we will focus in a lot of this course. Actually, that's not true. I should really expand that. This is the narrow view of computer architecture. We'll focus more on the logic as well over here. But if you think about computer architecture, this is the narrow view. But we'll focus in these three parts. Maybe we'll come to system software a little bit. But today, in most of today's systems, we really have a much more expanded view. So Google's Tensor Processing Unit is a great example of this, for example. You really need to know the algorithm and the devices and enable that algorithm to be executed on those devices. So understanding all of these over here will enable you to be a much better designer, both software and hardware. But of course, in this course, we're not going to be able to cover all of those clearly, right? We may touch upon some of them very briefly, but the fundamental part of this course is really over here. Okay, let's go into this a little bit more. So I said Richard Hamming is the person who said the purpose of computing is to gain insight. And this is the person. Did anybody know about Richard Hamming before? Okay, who did not know about Richard Hamming? I'll keep asking this question. That's good. Now you have an opportunity to learn more. So how did you know about him? Anybody? Yes. Hamming distance. Okay, that's good. That's good. He's famous for Hamming distance and Hamming codes. Yeah, he's famous for many things early on, theoretically. Okay, but let's, so we gain and generate insight by solving problems. We'll get back to Hamming in a little bit. So how do we ensure problems are solved by electrons? Basically what I said over here. But let me go a little bit deeper over here. So we transform the problem into an algorithm. An algorithm is essentially a step-by-step procedure that's guaranteed to terminate, where each step is precisely carried out, or precisely stated, and each step can be carried out by a computer. So guaranteed to terminate means it's finite. Each step is precisely stated means it's definite, and it can be carried out by a computer. It means effectively computable. You will see this in Pat and Patel book. I'm not going to go into detail, but this is really required for a computer to understand what your problem is, right? For example, if you ensure, if your algorithm is not, you don't guarantee that your algorithm terminates, then you have a problem, right? You have an infinite loop, maybe. Right? Each step needs to be precisely stated. That's important, right? So it's essentially a recipe, right? And it needs to be effectively computable by a computer, right? So I'm not going to go through these in detail. This is in your reading, but this is going to be important for you to know. And there are many algorithms for the same problem, right? They may all satisfy these properties, but they may have many different implications on the performance, energy, security, ... right? I mean, even from, for example, if I formulate the problem as going from here to Bahnhof Stadelhofen, there are many algorithms I can follow to solve that problem, right? One of them may be flying over there from here, right? And as long as I can ensure that these are satisfied and effectively computable, for example, I don't think jumping over there is effectively computable, right? At least by me. Maybe by someone else. So that's an example of effective computability. Right? So you need to guarantee these, but these have different implications. Okay, programming language, there may be many programming languages and programs built on them. I'm not going to focus on that a lot, but you've all programmed in some language, I assume. Which program have you programmed in the first semester? Which language? Java. What else? Okay, only Java. Okay. We'll need to talk about that. Java is good, but there are many, many programming languages, right? And they all come with different trade-offs, again, right? Java is very high level. Maybe it's easy to program, but it may not give you a lot of control of what's underneath. C is very low level. Maybe it's harder to program, but it gives you a lot of control in optimizing things. And there is a huge trade-off between these two, right? So here, in this course, we will look into a programming language that's very low level. I'll call this instruction set architecture, but it's really also a programming language. That's how you essentially program the computer. These are the instructions that the hardware understands. So ISA is essentially the interface or contract between the software and the hardware. What the programmer assumes hardware will satisfy. It's really everything related to that. For example, an add instruction. This is how you specify an add instruction. Register 1, register 2, and the result goes into register 3, let's say. So you have two source registers, one destination register, and you write the instruction that way. Yes?
Would this be what we call assembly?
So assembly is essentially what I'm just describing to you right now.
Yes.
This is called an assembly also, although, I mean, we'll get to that, okay? Yeah. So we'll look into a computer from that point of view. This is the interface or contract between the software and the hardware. What the programmer assumes the hardware will satisfy and what the programmer needs to know to write the language. This is essentially what's specified in a huge manual that's produced by the manufacturer of a chip. And it tells you how to program this chip. On top of this, you can build a programming language like Java, and Java gets translated into those instructions through all of these over here that I just lumped together. Compiler translates a Java, and Java has a runtime system, actually. It translates those high-level instructions that you write. For example, you're searching for a key in a hash table. You program with hash tables? Tell me a data structure that you're familiar with. Heaps. Okay, heap is good. Heap is good. So heap, everybody's familiar with heaps? Okay, good. Heaps. You manipulate heaps, right? Of course, the computer underneath may not understand heaps, but it understands add, load, multiply, move the data from here to here. So somebody needs to translate your operations on the heap. For example, if you're doing search on the heap, somebody needs to translate that search all the way into these primitives. And that's the compiler or the runtime system. Does that make sense? Okay, so there is a transformation hierarchy level over here that we're not going to talk a lot about, but we will cover very briefly. So you should keep that in mind. It's not the... Now, I'll stretch your mind a little bit. This is not the only way of doing things. You can actually design a computer that understands heaps. Heap could be something that is in the instruction set architecture. You can have a data structure saying heap, insert this into the heap, right? That could be an instruction in the assembly program. That's certainly possible. It doesn't commonly exist in today's architectures, but don't take that as a given for the future. There are benefits to that. If you have heap, operations on the heap as part of your instruction set architecture, what the computer directly interprets, now you don't need to do this translation as much, right? This can be very lean, very simple. You write the program and it directly executes on the computer, on the hardware. So maybe that's good. And we'll talk about those trade-offs when we talk about the instruction set architecture. Again, the fact that it doesn't exist today should not really prevent you from thinking that it might not exist in the future. That's another key point in this lecture. Future is very different from today. Remember my comment about systolic arrays. I'll give you another example. You know about arrays, right? Okay, good. So arrays, whenever you program an array, whenever you want to access an array, you have an index, for example, right? Now this index may be out of bounds of the array. How do you check that in Java? You compare it to the array size, right? Or do you do that manually? How many of you are good Java programmers here? Do you compare, so whenever you actually want to access an element in an array, do you actually check whether the index is within the size of the array? No? You guys have forgotten Java? Okay. There are some languages that automatically do this, that automatically check whether your index is within the array bounds, right? But there are some other languages like C where your index is not checked. You have to check it as a programmer. And if you actually access something that's outside the array, outside the bounds of the array, you can still get the value. Maybe, as long as you have permissions to that, right? So that's a design choice at the high level. Now, there used to be computers that actually did this checking, bounds checking of an array in hardware. Basically, you have an instruction, a complicated instruction, that basically takes as inputs the array, the beginning and the end, and the index, and it tells you, it gives you either the value that you're trying to access, or it says, sorry, you cannot access it because it's not within the bounds of the array. So the hardware can be designed to do this for you. And there have been computers that way. That's not true for many computers we have. In fact, there used to be this VAX architecture, virtual address extensions, which later transformed into alpha architecture, but it had three-dimensional array checking. So if you have a three-dimensional array, you actually need to do checks on all of the boundaries, right? X, Y, Z, all of those directions. And it had an instruction that enabled you to do all of this in hardware very, very quickly and very, very efficiently. Okay, so the ISA specifies what your hardware can do for you. And later we have the microarchitecture that implements that. So we're going to cover both of these in this course. Microarchitecture is an implementation of the ISA. How do you actually do it? For example, let's start with a simple add instruction. There are many, many ways of designing an adder, right? You can, let's say you're adding two 32-bit values. You can add all of the 32 bits in parallel, Or you can add 1 bit every cycle. So you do it over 32 times, 32 iterations. This has implications on your hardware. So if you do 1 bit at a time, bit 0, get the result, get the carry bit, and then do it for bit 1, get the result, get the carry bit, and then do it for bit 2, ... This is called a bit serial adder. Has anyone heard of bit serial adders? Okay, good, some of you. Where did you hear about this? Nobody? Yeah? Okay, that's good. So he built a computer once. That helps. So bit serial adder certainly is one way of designing it, and it's very simple, right? You don't need hardware that's large. So on the other hand, a lot of the adders that we have today are very complicated. They do all of this in parallel. 32 bits, all of the bits are added in parallel. Of course, you may not always be able to do this, right? Because some of the bits, some of the additions, like bit 1, if you want to add bit 1 of the 2 numbers, that is dependent on the result of bit 0, right? If both of the bit zeros are 1s, you get a carry out. You need to incorporate that carry out in the addition of bit 1. So there is a serial chain over here. But you can parallelize this also. You can speculate. We'll talk about that. You can say, oh, I'm going to compute both outcomes, assuming that, so you have an outcome assuming that the previous bit is 1. You have an outcome assuming that previous bit is 0. You design hardware to do both. And then when you really know the outcome of bit 0, you select the right answer. So that's one method of parallelization, right? And you do it for every bit. So of course your adder becomes huge because it's a dependence chain, but that's how you can do this addition in parallel. Now I've given you just 2 implementations of an adder, bit serial versus this hugely parallel, complicated adder. That's microarchitecture. This doesn't need to be visible to the programmer. The programmer doesn't need to know exactly how the adder is implemented, right? All the programmer needs to know is they specify an add and the result is correct. Of course, the way we implement this has a huge implication on how long it takes to do this addition. The bit serial adder can take 32 cycles, whereas the bit parallel adder can take a single cycle. So it can be much faster. But we will see that there are other trade-offs associated. Okay, so logic is digital logic circuits. These are actually the building blocks of the microarchitecture. For example, gates. You will get to be very familiar with these in especially the earlier lectures. We will talk a lot about digital logic. And we will really not talk about devices. We'll abstract everything as the transistor itself. Okay, so basically we'll cover, this is the real of what we will cover. We will cover this part. So let me finish with this slide in the last 2 minutes. I'll give you an aside over here, and then we will continue tomorrow. We talked about Richard Hamming, and some of you said Hamming distance is what he's famous for, and that's true actually. This is a paper that is written error detecting and error correcting codes. He's actually one of the earliest fathers of error correction, error detection. So he introduced the concept of Hamming distance. How many of you know the Hamming distance? Wow, okay, where did you learn this? Okay, that's good. So I don't need to tell you about this, that's good. Maybe I can ask you about it though. So what's the Hamming distance between cat and dog? Assuming you have the, yeah. 3, perfect, okay, you got it. Okay, so he developed a theory of codes used for error detection and correction. And I would recommend, I mean, we'll put a lot of optional readings for you. These are optional. And he was a researcher at Bell Labs for a long time. And this is a talk he delivered at Bell Labs after he was done, basically. And he talked about his principles for research, his principles of developing new ideas. And I would recommend that you take a look at this in your free time. Okay, this is a good place to stop. We will continue, we'll pick up from this and talk tomorrow. Thank you.